The Lockheed Martin F-35 Lightning II is the most advanced and powerful military jet in history. With stealth designed in from day one, the F-35 has an unmatched ability to evade enemy detection and enter contested airspace. Advanced electronic warfare capabilities locate and track enemy forces, jam radars, and disrupt attacks. Producing such a sophisticated aircraft requires equally sophisticated manufacturing technology. We are fortunate to be joined today by Geoff Carpa, robotic applications engineer at Lockheed Martin. Geoff has been with Lockheed since 2014. Last November, he was named one of 22 outstanding young manufacturing engineers by the Society of Manufacturing Engineers. Back in college, did you ever imagine that you would someday be designing state of the art automation systems to produce state of the art aircraft? What's it like?
No, I can't say I ever imagined working in the automation industry, let alone manufacturing fighter aircraft, especially considering I was studying construction for my undergrad. It was a goal in college at one point to become a fighter pilot. So I guess you could say this is the next best thing. I guess it depends on where I'm at in the production phase because I get to wear many hats in my position. It's like when I first started, I was more of I guess, a research engineer slash scientist because we're developing prototypes and trying to figure out, what a good solution to a problem is. And then I get to put on my systems engineering slash project management hat as we write out a specification for that solution to go get an automation system from a vendor, manage that all the way through design, fabrication, and acceptance testing. And the phase I'm actually in now on a lot of my projects is the integration phase. So got to put the scientist engineering hat back on as we work through the various challenges. So, right now the average day is coming in and figuring out, what is it that's not quite working the way it needs to, going in and figuring out what the issue is and coming up with a fix for it.
Okay, so you helped design a robotic system for drilling and fastening panels for the F-35. Tell us a little bit about that. How does it work and what was the impetus behind the project?
Yeah, so I've actually been able to work on quite a few robotic drilling systems since joining the team. One of them is a six-axis robot with a multifunction end effector on it. So what it does is it locates holes on F-35 panels, countersinks them, and measures them. Another system we have also uses a six-axis robot and a multifunction end effector, but it automates our setup fastener process. And what that does is it basically locates a Clico temporary fastener, which is what we use initially to hold parts together. It removes that, then uses its vision system to locate a near full sized hole. It drills and countersinks it to full size, and then it installs a flush fastener, all with one end effector before proceeding to the next point. As far as impetus, there was a lot of pressure getting those projects into production. Mainly, we had affordability targets that we needed to meet to achieve program goals, and we also had to do all of that in a very short time frame.
What were some of the challenges you encountered as you were developing the system, and how did you overcome those challenges?
So one of the challenges we encounter on most of our projects is as you know, we're in an existing production line that's been around for over a decade now. So the first challenge is being able to capture that well-established manual process and then translate that into an automated function. And this often results in creation of a new technology. So we often handle that by prototyping it first so that we can test it in our lab or in production until we can get it to either mature it or scale it up to a production version of that design. And another challenge that we faced, particularly on the projects I was on, is proving out that robotic system for operational use in production. So we do acceptance testing at the supplier and in our plant, but it can be really hard to do this without a full scale test article. For example, on the setup fastener robot I was talking about, it works on an F-35 wing, and it can be cost prohibitive, unfortunately, to make it a mock-up of an entire F-35 wing. So way we handled that is we created a smaller scale test article that we're able to go test on to verify the robot's function, its accuracy, repeatability, and the quality it was producing. And then once we checked all the boxes there, we then went and tested on the actual F-35 wing. And the way we did that is we chose, first we would turn off all the robot's processes and we run the robot program just to make sure the robot motion is good, make sure it doesn't hit anything. And once that is good, we chose a small subset of holes to go process, and we did it very slowly, inspected it every step along the way to make sure everything was good. And then as that data continued coming back in good, we would do it a bit faster, do a larger subset of holes until eventually we were able to process the entire wing. So another critical enabler on these two projects was robot vision technology. And what that allows us to do is account for the variability we often see from wing to wing. And it helped us to greatly improve our accuracy because it's able to go locate the actual locations of features on the wing. For example, on the setup fastener robot, we have holes that are manually drilled by the mechanic before it gets to us. And the vision system is always able to find the center line of those holes and overcome that variability. Uh, that same robot system also uses the vision system to locate existing features on the wing that it can use the data from to find its alignment to that part when it comes into the cell.
Okay, do you see the role of robots increasing in aerospace manufacturing?
For sure, especially as we continue striving towards determinate assembly, which is um, basically assembling the parts already drilled versus drilling them during assembly. So the aerospace industry is able to capture a lot of data these days on the as-built parts. So we're able to use that to create a digital twin of the final product, and that is a crucial step towards determinate assembly. And the end goal of basically being able to assemble an aircraft like a Lego set. And so also robots are getting more accurate. They're getting more mobile, more adaptive. So you combine that with ready to assemble aircraft parts, and I can see a factory where robots are assembling aircraft. Um, However, I think we will always depend on mechanics to some extent, especially for some of the more intricate tasks. But that also opens up the opportunity for collaborative robotics, where mechanics will basically be able to work with robots to complete those processes.